Welcome students. I am P. Manivanan, Assistant Professor, Department of Mathematics, Government College of Engineering, Srirangam. In this video, we discuss the portion characteristic of a ring and theorem on finite field for the BE Computer Science and Engineering students, third year, fifth semester, paper MA8551 Algebra and Number Theory, Unit number 2, Finite Field and Polynomials. First, we define the characteristic of a ring. Let R comma plus comma dot be a ring. If there is a least positive integer n such that n r is equal to 0. Here z is the 0 of the ring R. That means additive identity for all r belongs to R. N into R equal to 0, then n is called the characteristic of the ring R. Then we say that R has characteristic n, and we write characteristic of R equal to n. When no such integer exists such that nr equal to z, there is no such integer exists such as this, then R is should have characteristic 0. No such integer exists, then R is should have characteristic 0. Example, the ring z3 comma plus comma dot has characteristic 3. Since z3 have the elements 0, 1, 2. If we multiply 3 with each and every term, 3 into 0 equal to 0. 0 is the additive identity. Okay. Then 3 into 1 equal to 3. 3 is equivalent to 0 under mod 3. Under mod 3. Then 3 into 2 equal to 6. 6 is equivalent to 0 under mod 3. Therefore, 3 into all the elements in Z3 will be 0. Therefore, the characteristic of Z3 comma plus comma dot is 3. Similar way, Z4 comma plus comma dot has the characteristic 4, and in general, Zn comma plus comma dot have the characteristic n. Second example, the ring Z comma plus comma dot and Q comma plus comma dot have both characteristic 0. And also R comma plus comma dot complex number C comma plus comma dot are also have the characteristic value 0. Since there is no such integer such that n into some q value is equal to 0. There is no such integer in q. There is no such integer in all the sets like as n into x equal to 0. There is no such integers exists satisfies these conditions. Therefore, the given rings are characteristic 0. Third example, a ring can be infinite. Ring can be infinite. These rings are infinite. Its characteristic will be 0. A ring can be infinite, still have positive characteristic. That means some characteristic value is exists. For example, Z3 of x is an infinite ring. It is an infinite ring. But Z3 is finite. Z3 is finite value. But Z3 of x, the polynomial ring is infinite ring. But its characteristic value is 3. Since Z3 of x, all the polynomials with 3 into some value must be multiple of 3, it is equivalent to 0. So Z3 of x is an infinite ring, its characteristic value is 3. Note, the order of a finite ring Z2 of x divided by x square plus x plus 1, that is the quotient ring. This will be different from its characteristic. Its order is different from its characteristic. here its order will be, it have z to have two elements, its order will be 2, the order be q power n, it is equal to, it is q, it is equal to n, so 2 squared equal to 4, so it have the 4 elements, this quotient ring. But the characteristic of this polynomial, the numerator is z2. If we multiply each and every term by 2, the answer will be 0. The answer will be 0. Hence, the characteristic value is 2. Theorem 1. Let f comma plus comma dot be a field. If characteristic value of f be greater than 0, then characteristic value of f must be prime. In this proof, we write the unity of f as u, that is distinct from the positive integer 1. Let us assume characteristic value of f be n and it must be greater than 0. We want to prove it be a prime. On the contradiction that n is not prime, let us assume, then if it is not prime, then it is composite number. What is the meaning of composite number? It is a multiple of two numbers between 1 and n. Both numbers will be greater than 1 and also less than n. By the definition of characteristic, the characteristic value of is n. Therefore, n into u equal to z. N into u equal to z. Here, z is the 0 of f. Replace n by mk. So here replace n by mk. Mk into u equal to 0. But we know that mk into u equal to, what is the meaning? Mk times u. Mk times u. U is the identity element. It can be rewritten as m times into k times, since u is the identity, multiplicative identity. So we replace this as this multiplication. So mu into ku, mu into ku, mk equal to u. Sorry, mk into u. We know that mu equal to m, ku equal to k. It is equal to mk. So mk equal to m into k. Replace this mu into ku like this. Since f is a field, every field is an integral domain. Every integral domain have no zero divisors. Using 2 in 1, replace mk into u by mu into ku. So mu into ku equal to 0. It has no zero divisors. Therefore, either mu equal to 0 or ku equal to 0 by the no zero divisors condition. Assume if there is loss of generality, let us assume ku equal to z. Ku equal to z. Then for each r belongs to f, kr is equal to, r is replaced by ur, since u is identity element. By the associative law, it can be rewritten as ku into r. Here ku equal to z, so it is z. Z into r equal to z. It is the contradiction that the choice of characteristic value of f will be n, but here k into r is 0, therefore the characteristic value will be k. Here k is less than n, so it is the least positive integer is k. It is the contradiction to the characteristic value of f will be n. Hence, what is the contradiction? Let us assume n is not a prime. It is the contradiction. Therefore, characteristic value of f will be prime number. Theorem number 2. A finite field f has order p power t, where p is prime and t belongs to z plus. T belongs to z plus is positive integers. Given f is finite field, let characteristic value of f equal to p. Since by the previous theorem, field have the characteristic value must be prime number. Therefore, characteristic value of f equal to p. Let us assume u denote the unity, z denote the zero element of the field. First, let s naught equal to u comma 2u comma 3u and etc. up to pu. Pu equal to z. Since characteristic value of f equal to p, therefore p into any terms will be 0. So pu equal to 0. It is a subset of f. Let us assume s naught will be a subset of f. Claim number 1. Elements of s naught all are distinct. These elements are distinct. To prove this claim, assume the contrary that mu equal to ku. For some value mu equal to ku. Here m and n values are lies between here u into 1. So 1 to here p. So 1 to p. 1 is less than or equal to m, less than n, less than or equal to p. Here n is crudest value, so n minus m, subtracting this, taken mu taken to that side. What is the answer? N minus u equal to 0. 0 is the zero element of this field. With n minus m, here n is greatest value, m is smallest value, so n minus m is lies between 0 to p, not here equal, since m is greatest value, n is lowest value from these two values. So for x belongs to f, we now find that n minus m into x multiply with x. What is the result? N minus m into x is equal to n minus m into x is replaced by ux. By the associative law, we interchange the bracket n minus m into u. What is the value for n minus m into u? N minus m into u is 0. So it will be 0. N minus m into u will be 0. 0 into x is 0. It is the contradict that characteristic value of f is p. Here n minus m is less than p. It's multiplied with x. The answer will be 0. Therefore, it contradicts the characteristic value of f. Therefore, what is the contrary? Here we assume mu equal to nu. It is the contradiction. Therefore, the elements of S naught all are distinct. Therefore, the elements of S naught are distinct. Hence, S naught contains exactly here how many elements? 1, 2, up to p. So, S naught contains exactly p power 1 elements. If S naught equal to p, then order of p equal to p. Hence, the theorem is proved with n equal to 1. If not, what is if not? S naught is not equal to f. That means S naught is not contained in f. Let us assume A belongs to f with A not belongs to S naught. A is not belongs to S naught. Here, let us assume S1 equal to the collection of MA plus NU. MA plus NU. Where m and n value is greater than 0 but less than or equal to p. This S1 is contained in f. Contained in f. Then S1 contains at most here m value 0 to p. Not here 0. So 1 to p. So p into p. The total possible values is p squared elements. Therefore, S1 contains at most p squared elements. Claim number 2. The elements of S1 are distinct. The elements of S1 are distinct. To prove this claim, assume the contrary that two different values will be equal. In S1, M1 into A plus N1 into U, it is the element form in S1. It is equal. Here M1 and M2 value be greater than 0 but less than or equal to P. And at least one of M1 is not equal to M2 and N1 is not equal to N2 is true. Subtract, we replace this value by interchange M2 taken this side, N1 taken to that side. Then this equation rearranged as M1 minus M2 into A equal to N2 minus N1 into U. It is equation number 1 with at least one of M1 minus M2 and N2 minus N1 is non-zero. At least one is non-zero. First case, let M1 minus M2 equal to 0, N2 minus N1 is not equal to 0. In this case, we assume this value be 0, this value be not equal to 0. Therefore, it is not equal to 0, which implies M1 minus M2 equal to 0. Therefore, this value be 0. So, N2 minus N1 into U equal to 0. 0 is here is Z. Therefore, N2 minus N1. N1 and N2 are not equal. Therefore, N2 minus N1 value B lies between 0 to P, greater than 0 and less than P. For all x belongs to F, N2 minus N1 modulus of N2 minus N1 into x is equal to modulus of N2 minus N1 into U. U is the multiplicative identity. So multiply with U. Then what is its value? Here N2 minus N1 value be modulus of N2 minus N1 into U is 0. Therefore, it is value be 0. 0 into x is 0. It is the contradict to minimality of P. Since N2 minus N1 into x is equal to 0, therefore, the characteristic value of FB N2 minus N1. N2 minus N1. It is the contradiction to the minimum value of P. That means characteristic value of P. So, it is the first case. M1 minus M2 equal to 0. N2 minus N1 equal to not equal to 0. We interchange the concept. So, let us assume N2 minus N1 equal to 0. M1 minus M2 is not equal to 0. In the similar way, N2 minus N1 equal to 0. N2 minus N1 equal to 0, which implies M1 minus M2 into A equal to 0. With A belongs to F, 0 belongs to S, and A not belongs to S. These are the assumptions. Hence, and also M2 minus N1 value must be less than P, which implies A not equal to 0, A not equal to 0, and A belongs to F, A belongs to F, which implies A inverse exists. A is non-zero element in the field, then inverse of A is exists. Since every non-zero element have the multiplicative inverse in a field by the definition of field. From 2, multiply A inverse on post multiply by A inverse. So M1 modulus of M1 minus M2 into A inverse equal to Z into A inverse. Z into A inverse. Z is 0. 0 into any value will be 0. Therefore, A into A inverse equal to U. It is the identity element. Therefore, M1 minus modulus of M1 minus M2 into U equal to 0. It is the contradiction. What is the contradiction? M1 minus M2 into one element will be 0. Then the characteristic value of the field is M1 minus M2. M1 minus M2. Here let us assume x belongs to F. by the previous property. This is the contradiction to the minimality of P. The previous two cases, either M1 minus M2 equal to 0 or N2 minus N1 equal to 0. We prove the contradiction parts. In this case, let us assume both value be not equal to 0. Therefore, M1 minus M2 into A equal to N2 minus N1 into U. This value be not equal to 0. Choose K belongs to Z plus such that K value be less than P. Therefore, K into M1 minus M2 will be equal to 1 mod P. Choose K any one value satisfying this condition. M1 minus M2 into K equal to 1. That is the M1 minus M2 inverse is K. Therefore, A equal to multiply this term A on both sides. So, A equal to K into M1 minus M2 into A equal to M1 minus M2 into A equal to M1 minus M2 into A equal to N2 minus N1 into U. So N2 minus N1 into U, which implies A belongs to S, which implies A belongs to S. It is a contradiction. Thus, claim number 2 is proved. So all the cases are contradiction. Therefore, S have exactly p squared elements. Therefore, there is no two elements are equal. Therefore, S1 contains exactly p squared elements. If S1 equal to F, then the theorem is true with n equal to 2. If S1 not contained in F, then choose an element P belongs to F but B not belongs to S1. Continuing the above process with S2 equal to LB plus MA plus NU, where 0 less than L, M, N less than P. Then S2 contains exactly P cubed elements. In similar way, since F is finite, we reach a set of Sn-1 containing Sn-1 containing exactly p power n elements. Here n minus 1. S2 contains p cube. S1 contains p squared. So Sn minus 1 set contains exactly p power n elements with f equal to Sn minus 1. Hence f contains p power n elements. Hence the proof. The last example. Find the orders n for all field Gf of n, where n lies between 100 to 150. We know that from the previous theorem, a finite field have order p power t, where p is prime, t belongs to z plus. What is the value of z plus? Z plus is 1, 2, 3 and etc. Positive integers. We know that the prime numbers between 100 to 150 are 101, 103, 107 and etc. to 149. Also, we observe that 2, 5, 11 are prime numbers such that 2 power 7 equal to 128. 120 is lies between 100 to 150. And power 7 belongs to Z plus. Similar way, 5 cube equal to 125 lies between 100 to 150. 11 squared is 121 lies between 100 to 150. Therefore, the required orders are the prime numbers with the prime power t elements. Hence, the required answer is this. Thank you. Thank you, students.